In this episode of FUM0014 machining, we are going to talk about electronics. This has to do with machining, but it's mostly electronics this time. Later on it will be something tangible. Today it's plans and design and not very much physical content. So if you are not into electronics, and especially if you are not into microcontrollers, and you don't want to know anything about those things, well, you are better off, because it's going to be heavily microcontroller oriented. So, of course, first things first. Let's start with this one. Okay. While I'm drinking this, think about if you are continuing or not. So, okay. This is a picture here in my wall, and I would like to present what it is. It's a means to against chatter. Well, in a lathe, normally when you are machining something in your lathe, you can get chatter. It's sometimes you get away really easily just by slowing down or adding pressure on your tool, or there are multiple of ways doing this in the traditional way. But sometimes, especially if you have a component which is which is like a bell. Well, if you're machining a church bell, it will be most certainly starting to ring. And there is it's a sum of certain things. First of all, there is it's a resonance. Chatter is always a resonance. It means that you have a positive feedback. It means that it tries to push it into the same way, not counteracting. And it's a sum of your workpiece, your lathe in total, and the rigidity of your tool post and the tool in your tool post. Sometimes the only component that is ringing is the tool itself. Yeah, and well, you can enhance the rigidity of your lathe somewhat, quite a lot actually. You can enhance some of the rigidity of your tools there, but there is a limit to how much you can do. And then there is this thing you can actually do. If you have ever worked with a VFD, you have noticed that if you slightly change the speed, the chatter will go away momentarily, but it will come back quite soon. So you have to be changing the speed back and forth all the time, and well, of course, if you don't have a VFD, this is not possible. Maybe breaking the spindle somehow, yeah, okay, but it's really tedious. So what this thing does is it's actually a thing with 3 buttons and 3 knobs. You select your speed, you select how much does the speed change, and then you select how fast, what is the frequency, how it changes. Okay, and well, you can do this analogically. Yeah. In my case, because I'm a programmer, So I will do it with microcontroller, which is in this corner here. This small picture here is the VFD, in my case 1 yuan. And then these here are the buttons and the 3 potentiometers which one can use to control the thing. Now what I'm going to do, I'm going through all the components here in detail, what they do, why they are there, and so let's start. Well, I will put a picture somewhere in this region to enhance the quality. You cannot probably see this ordinarily, this is too small. Okay, first things first, the connections to the VFD. This VFD I'm talking about has possibility to control it outside by means of push buttons. Okay, but there is one caveat in that one. I don't remember quite exactly which one it was. I believe it was the stop button, which has to be pushed on in order to get it running. Go figure. But well, for this reason, I don't connect the buttons directly into this. They are connected using MOSFETs. Actually, we have 4 MOSFETs, and now you will be getting a picture about the controller and the MOSFETs. In addition of these MOSFETs, this button interface, this Huanyang has a voltage sensitive input. The higher the voltage, the faster the motor runs. And the range is from 0 to 10 volts. And then you have, in this VFD, you have a 12 volt output. It's rated 200 milliamps, so 0.2 amps. This one, the whole thing takes about 20 milliamps, and this 20 milliamps is, it's overrated. The actual figure is around, I believe, more or less 13. So it's almost double what this actually consumes, what I have estimated, but it's still 200 milliamps is 10 times more than 20. So it shouldn't be any trouble of using the power supply from the Huanyang VFD. Okay. These FETs are normally open or closed, depending on how you configure it. But I know from experience that if you leave them open, the VFD will not run. So if you switch it on, it won't run. Yeah, that's it. So for this reason, I have included here gate resistors. The FET is an element which switches on when there is this type of FET. Switches on when there is a positive voltage in the gate. This particular type is so-called low voltage FET, which means that the gate doesn't need to go very high. Something like 4 volts is enough to put it in short circuit. So therefore, I have replaced the actual buttons with 4 FETs. Okay. Well, there is a reason for this, and of course you can control those FETs with the microcontroller. Well, that's one thing, how you control this. And then you have the control voltage. it's coming from through an LPF low pass filter. This means that anything above 200 Hertz, this is 4 times your ordinarily, maybe less than 4 times if you are in America. In Europe it is 50 Hertz, so it's 4 times the normal frequency in your power outlets. So this is designed to be 200 Hertz. Anything above that will be filtered away. And why is this? Okay, the MCU microcontroller can only deliver ones and zeros. Yeah, it doesn't know anything about the DC levels and output, etc. But you can do it in a nice way using so-called PWM, pulse width modulation. This one means that there is a ratio, how much of the time the output is high at 5 volts and how much of its time it's down at 0 volts. If it only goes up for a very short period of time, then stays low longer, and then again and again, very short periods of time, the average of these two states is quite low. On the other hand, when it's staying half of its time up, half of its time down, etc., doing 50-50. Well, the average is 50. And then the other way around, when it's becoming so that it stays up most of its time, only occasionally going down for a very short time, then the level is high. But these microcontrollers operate at 5 volts. So at this point, in input of the filter, the voltage can at its highest value be only 5 volts. Obviously that is not enough. We need to amplify it. So at first we want to get rid, there is this capacitor, it's quite small. Actually all the components in this one are really small. They are SMD, surface mount device, which is, well, they are really small. You can see them, but you have to use magnifying glass. Okay, the first capacitor and the resistor, their purpose is to take away very rapid voltage movements, because the operational amplifiers, this is a double, it's a cheap one, can't handle that kind of things. So you have to take away the highest frequencies before you even try to do anything with this. And the actual amplification happens here. It just doubles it. Operational amplifier is a device which wants to keep its plus and minus inputs equal. So if the plus input goes high, the minus input, the output goes high as well, very high. And if the minus input goes as well high, so when it reaches the plus input, when they are equal, then the output starts to go down again. Well, this is negative feedback, you can do it. But, well, let's assume we have this 5 volts in the positive input. So, there are 2 equal resistors here, and if we have 10 volts here, how come? We have 5 volts on the negative side too. So, it amplifies by 2. It's a, well, It's an easy thing to do, and it's really common sense. Next thing, this is Butterworth low pass filter. It's designed for 200 Hz, and if you look at the values of the components, you can quite soon see that they are almost always the same. That's a very good practice. I have tens of thousands of resistors with these values back home. So I don't want to use different values. I designed these in a way that I can use these just a few values. You can do that. So the PWM frequency in this case is about 1 kHz, and this filters it out and leaving only the DC component. So at this point where it's going into the VFD, it's a voltage that's steady, and in this point where it comes out from the MCU, it is rapidly changing, but it has a relation between the high and low voltage times. Okay, so this way you generate a DC voltage into the for the VFD. Well, the next component here, which is often very much overlooked, and everybody relies on the reset mechanism of these microcontrollers. In my opinion, well, as good as they might be, they are not very good in accuracy. If the voltage goes down, they won't reset every time in the same place, and sometimes they struggle. I mean that it resets, lets the MCU run, resets again, and this happens in a rapid fashion, and you are getting a lot of interference everywhere, and nothing seems to work. I have seen that to happen very often. So therefore, this little guy here, it's voltage watcher. When the voltage goes below 4.7 volts, it will lock up. It will put the reset so that this goes into reset state, everything locks up, and it will stay there a minimum amount of time for the first, and then again it will come back from its reset state only when the voltage is a little bit above 4.9 something, I don't remember how much it was, but this one works really well. I have had no trouble with that one. It makes your device very interference tolerant in that way. Then there are some, this particular microcontroller has analog to digital converter. It has 8 channels for converting analog signals into digital signals. In our case, the analog signal is these 3 potentiometers here, one for speed, one for modulation frequency, or how fast the speed varies itself, and the third one is how much it varies. So 3 potentiometers, their inputs, and they are filtered. One practice here, which is not obvious from the schematics, but if you look carefully, I put a picture, you can see it's AGND. It means analog ground. So I separate the digital ground and the analog ground from each other. This is a very good practice, and how it is separated, there are resistors here. They would not normally be needed, but they are for the separation. And then we have small capacitors which connect the AC I mean not DC but AC component is connected to the analog ground. And this makes it quite immune for external interference again. Well, the next thing is the power supply itself. In Huanyang there is a point where you can get 12 volts out from there. And these 12 volts, I don't trust it. Well, I trust it's 12 volts, but I don't trust the quality of that. It might contain whatever hairy components, this voltage. Therefore, I have here a choke. It's an inductor. It's very small. It's only 470 microhenries, but it's enough to filter out most of these disturbing interferences. And furthermore, I have a very specific capacitor here. It seems like an electrolytic capacitor, but it's not. It's OSCON. This is something like a tantalum capacitor, but it has very low series resistance. This means it's a very good capacitor. Quite simple. So a good capacitor. Next step is a voltage regulator. This one simply takes the 12 volts from here and regulates it down to 5 volts. VCC in this schematic means 5 volts. VC means 12 volts. So actually the operational amplifiers use 12 volts and the MCU and the power watcher use then this 5 volts. Furthermore, the analog supply for the analog to digital converter needs additional filtering, and also it needs a separation from the actual ground to the analog ground, and this one is done by a small inductor and a capacitor. And on every supply pin I have put an extra ceramic capacitor here. They are small, and I believe I have 10,000 of those, so that's just makes the circuit board a little bit well, crowded. So basically that's it. It's quite simple thing. You just push the run button. It will then switch on and off these FETs there in a specific way so that the VFD runs. You push the run reverse button and it will do the same, but in a way that the motor is running reverse direction. Then you push the stop button and it will stop. And then you have these 3 knobs for speed, then speed variation, frequency, and speed variation amount. That's it. Well, I hope you enjoyed this small presentation of my plans of doing this chatter eliminator. It doesn't eliminate the chatter totally, but it makes it easier to deal with it. Yeah. Till next time.